Right, so given the problems with the ether hypothesis, various people tried to solve these problems, obviously. And Einstein noted that you could come up with a new way of describing space and time which would solve these, which would be able to explain these experimental results without having to use the ether. Okay, and this is the theory of special relativity, so this is what we're going to start looking at this time. Okay, so Einstein's observation was that it was enough to explain these results. It was enough to make two assumptions about the nature of space and time, which I'll state now. So these assumptions are known as postulates of special relativity. Okay? So a postulate is kind of like an assumption or a principle, okay, an idea for this theory. Okay. Okay, and today's class is basically going to be focusing on these postulates, what they are and what they mean. So the first postulate is something known as the principle of relativity. Okay, from which the theory of relativity gets its name. This is not something that was discovered by Einstein. This is a principle that was first described by Galileo a long time ago. Okay, so this principle of relativity is very old, but Einstein made use of it in a new way. Okay. And the second one is that the speed of light should always be a constant. So to be specific about what does it mean, the constant speed of light, the speed of light should be constant if you are in a vacuum and this is true for all inertial observers. So these conditions are important. The speed of light in air is actually slower. Okay, as the light moves through a medium, it slows down. The speed of light in water is even slower. Okay? So the constant speed of light is something that's only true in a vacuum, okay, when there's no matter. And also, this inertial observer condition here is important, and later on I'll say exactly what this means. What is an inertial observer? Okay. Right, so these are the two postulates of special relativity from which the rest of the theory follows. So I'm going to spend a bit of time to focus on both of them and say what they mean. Okay, so we'll start with this principle of relativity. Okay, so we're going to have to talk quite a lot about the principle of relativity, so I'm going to abbreviate it to POR, okay? Principle of relativity. Right, it says the following. Suppose that I've got an experiment. Doesn't matter what the experiment is, it can be anything. So I do an experiment here, okay? And then somebody else performs an identical experiment. These two experiments are identical, except the second experiment is performed at a constant velocity relative to the first. Okay? So for example, you could imagine putting this experiment on some kind of train. Okay. Again, my drawing skills are not very good, but anyway, you get the idea, right? So you put the second experiment on some kind of train, and then you move it with a constant velocity u relative to the first. Okay? So you have two identical experiments, but the second is performed at a constant velocity relative to the first. What the principle of relativity says is that the results of the experiments will match. Okay? So whatever the result of this experiment is, this experiment will have the same result. In other words, moving at a constant velocity does not change the result of any experiment. So let me write that. So an intuitive way of thinking about this is if you've ever been in an aeroplane. Okay? If you're in an aeroplane and it's just traveling with a constant speed and the windows are closed, you can't tell that you're moving, right? On the inside of the plane, if you get up and walk around, it feels exactly the same as if you are stationary on the ground, right? You can't tell the difference. And that's basically what this principle is saying. You can't tell the difference between being stationary and moving with a constant velocity. Okay. Right, so that's the statement of the principle. This is an example of what is known as a symmetry of physical law. Okay? So I want to explain a bit more about what that means. Whenever I do this kind of square bracket, by the way, it means that I'm making a side remark. Okay? So an extra bit of information to go along the main text. Okay, so what is a symmetry of physical law? You should be used to the general idea of symmetry, right? A symmetry is something that you can do to an object that doesn't change its appearance, right? So for example, if I take a rectangular piece of paper like this has a rotational symmetry, right? I can rotate it by 180 degrees and it doesn't change in appearance, right? That's the idea of a symmetry. So an idea of a symmetry of physical law is analogous. It means there's something we can do to an experiment where the results will not change. Okay? The behavior of the experiment will not change. So this is an example. We can take the experiment and move it with a constant velocity and it doesn't change the behavior. Right? So there are other examples of symmetry in physical law as well. The most obvious ones are the translation symmetry, right? Which is basically if I perform an experiment here in Seoul, or if I perform an experiment in London or New York or wherever, then that doesn't change the results of the experiment, right? Unless the experiment is specific to your position. So that's a translation symmetry of physical law. Okay? Another one is a rotational symmetry of physical law, which says it doesn't matter whether you set up your experiment like this, or if you turn it through 45 degrees, right? Rotating the experiment, again, does not change the results of the experiment. Okay. Okay, and I said there's some other examples of this. So the two I mentioned are the translation symmetry and the rotation symmetry. Okay, so given that we've stated this principle then, we can ask, well, how do we know that this is true? Right? How can we check it? Well, you can check it experimentally as described here, but I want to also look at the theories. So suppose we've got a theory of the world, like Newton's theory of motion, right? Newton's equations of motion. How can I check that those equations, that theory is compatible with this principle? So how can I check that Newton's laws of mechanics are compatible with this principle? Okay. And so that's what I'm going to explain now. Okay. So I'm going to show you how to do this for a particular example of Newton's laws. So I'm going to look at the case of conservation of momentum. How can we check that Newton's law of conservation of momentum is compatible with this principle of relativity? So first of all, we need to think of an experiment that tests conservation of momentum. Okay? So you can imagine whatever you like. I'm going to imagine an experiment where I've got a box filled with particles. Okay, and these particles are all moving around like this, and they're bouncing off each other and exchanging momentum. Okay. So I'll call the masses of these particles mi. I is the index of the particle, and the velocity of the particles I'll call vi. I've got particles with masses mi, velocities vi. Okay. So then the total momentum, according to Newton, is just the sum over all particles of the mass of the particle times the velocity of the particle. Right? That's Newton's definition of momentum, right? Okay? Right. If you want to be completely specific, you should really include the momentum of the box as well, because the particles will be exchanging momentum with the box. But anyway, that's not an important complication. Right, so in this experiment, what does conservation of momentum mean? Okay. It means simply that the momentum I measure at a certain point in time will not change if I measure it at a later point in time. Right? So it means that the momentum at time t1, which I can write as this, should be the same as the momentum at another time t2. So I can write down conservation of momentum as an equation like this. Okay? Total momentum at time t1 should be equal to the total momentum at time t2. Now, what the principle of relativity says is that this result should not change if I put the experiment on a train and move it with a constant velocity. Right? So again, I do the same experiment as before. Here. So this is experiment number 2. Experiment number 1, let's say. Okay, so it's exactly the same experiment. Okay, initial velocities and everything are all the same, except I put it on a truck. Okay, and I move it with a constant velocity u. Okay, so because I'm moving the experiment, the velocities here will change, so I'll call the new velocities vi prime. Okay. And the masses mi. Masses don't change, as far as we assume, right? So masses mi, velocities vi prime. Okay. So then again we have to ask, how are the velocities vi prime, that's in experiment 2, related to the velocities vi, which are from experiment 1. Okay. How can we relate the velocities in the second experiment with the velocities in the first experiment? Okay. Now, one possible way of doing this is to use the Galilean transformation. Right? The Galilean transformation tells you how the velocities, if I shift everything by a constant velocity, how the velocities here should be related to the velocities there. Okay? And what it said is that vi prime should be equal to vi plus u. Right? So we just shift all the velocities by u, according to the Galilean transformation. Okay? So then we can check what this conservation of momentum means in the second experiment. Okay? Okay, well, let me do it this way. Okay. So if experiments 1 and 2 have the same results, okay, which is what the principle of relativity says they should, then you have the VI at time t1, VI prime at time t1 is equal to VI at time t1 plus u, okay? And you also have that VI prime at time t2 is equal to VI at time t2 plus u, okay? And I can put both of these definitions into this formula for conservation of momentum. And hence, the total momentum at the beginning of experiment 2, that's the sum upon I, mi vi prime time t1, this is the same as the sum upon I, mi vi time t1 plus u. Okay, just using that, which is the same as the sum upon I of mi vi time t1 plus the sum upon I of mi u. Now we can use the conservation of momentum in experiment 1 to write this as the sum upon I mi vi time t2 plus the sum upon I of mi u. Okay, and then you can just work backwards. So then you can write this down as the sum upon I mi vi time t2 plus u. And then finally, this is the sum upon I mi vi prime t2. Okay? And what's this? This final line is the statement of conservation of momentum in the second experiment. Okay. So actually it's a very simple, almost silly calculation, but it shows you something important. What it shows you is if conservation of momentum is true in the first experiment, then it's also true in the second experiment. Right? And this is how we can check that Newton's laws are compatible with the principle of relativity. Right? If momentum is conserved in this experiment, then it will also be conserved in this experiment. Okay? That's what this calculation here shows. We use the conservation of momentum in the first experiment to show conservation of momentum in the second. So that's how you can check that a given set of physical laws are compatible with this principle. Right? If they predict a certain result in this experiment, and I shift all the velocities by a constant amount, then they predict the same result in the second experiment. Okay? They predict the same results in both experiments. Okay. But notice, and this is the important point, in order to be able to derive this result, we had to make use of the Galilean transformation. Okay? So this idea that Newton's laws are compatible with the principle of relativity depends on the use of the Galilean transformation. which will very soon turn out to be significant.